instead of doing the video, let me do the PowerPoint and see how that works. I already recorded this once, but I guess it didn't work, so I've got to record it again for the online people. Let's see. Chemistry. Oh, that's loud. I'm thinking about, not thinking about. What do you want from me?
It says no.
I know. That's the no sound. That's the like, no, you can't do that sound. Chemistry. There we go. But I've been approved to buy a new 3D printer, and now I'm having cold feet, and I don't know if that's. Yeah, I don't know if that's the one I want to buy.
Why buy a new one?
Because these are old, and actually I had to fix this one yesterday, and I fixed it, and it's messed up now. I fixed the problem that I had, but I apparently created another problem. And so these are old. They were here when I got here, so I don't even know how old they are.
How many years have you been here?
This is my 5th year here. So, and some of y'all like don't even keep your cell phones that long. So,
I do.
Dang.
well, I do too, because cell phones are expensive, and
Yep.
you don't have to buy new ones all the time. So it's just playing games on it mostly. Playing games and sending texts, like you don't need a brand new cell phone all the time. But anyways, I'm looking at getting a new 3D printer and trying to make sure that I'm buying the right one and not buying one that's going to be like a waste of time. So, but I think I got a pretty good one picked out, and I can make it work. So today we're going through an extremely long named assignment. I don't know why they just didn't name it something else, but it's called metals, nonmetals, metalloids, noble gases, halogens, alkali metals, alkali earth metals, transition metals, lanthanides, and actinides. That's like the whole name of the assignment. So everybody close your Chromebooks. I know you want to work on it, but I want to go through this because we're going to use this over and over again for a couple different sections. So in first period, I did the video on this, but I think I should be able to get through it a little bit faster and kind of hammer home the stuff that you need to know about this. So everybody has a periodic table? Yeah, you'll need your periodic table. So get that out because we're going to look at the different types of elements. So they mentioned this little stair step on your periodic table. On yours that you have, what color are these elements?
Green.
They're the dark green ones, yeah. They're the dark green ones. These are going to be your dividing line between your two major parts of the periodic table. So everything to the left of these elements are metals. Everything. The light blue, the pink, the yellow, the orange, the gold, the green. Everything to the left is metals. Everything to the right is nonmetals. The light green, the teal, and the dark blue. So what do we have more of? Metals or nonmetals? We have more metals, way more metals, only a small group of nonmetals. And then as you'll find out in just a little bit, these in between that are the dividing line are metalloids. They kind of act like metals and nonmetals. They're a little bit of both. So metals are to the left, nonmetals are to the right, and these elements are your like dividing line, this little stair step color green. What they say, and you're going to see this as we go through, behavior of elements, like what your element's going to do, what it's going to act like, its properties can be predicted by where it's at on the periodic table. That's the whole point. This is not just like a list of elements. It's an actual table that shows us what the elements can do, what their properties are. And so if you learn how to read about it, this will help you out moving forward. So they're going to start with metals. Metals are found on the left side of the periodic table. Really, you can see there's so many metals. They're found on the left and in the middle. Everything to the left of that little green stair step is going to be metals. Metals lose electrons to form cations. So first, if I lose an electron, what charge is an electron? Negative. If I lose a negative charge, what charge am I going to be left with? A positive. And positives are cations because positives have T's, cations have T's. That's your name for a positive ion. So when I lose an electron, I'm positive and I'm called a cation. And the reason metals lose electron, there's lots of reasons, but let me grab one of my own instead of using yours. They don't have very many electrons in their outermost shell. So like over here, my alkali metals and my alkali earth metals, let's just use this first column. How many electrons do they have in that outermost shell of 8? They only have 1. Is it going to be easier for them to steal 7 more electrons to fill up and get to 8? Or is it going to be easier for them to just let go of one and let somebody else take it? Yeah, they're just going to get rid of one. And any atom they bump into that needs an electron, they're just going to be like, here, I've got extra electrons, just take this one. It's not a big deal. So they're very easily going to lose that electron. When they lose that last electron in that outer shell, it's now empty, doesn't have any electrons in it, so essentially doesn't exist. You go down to the shell below it, and they're full up with 8. So by getting down to 0 and losing electrons, they really go down to the next shell and are filled up with 8. So now they're nice and happy like the noble gases over there. So metals lose electrons to form positive cations. That's what they do. What else can we describe metals as? Lustrous. What does lustrous mean? They're shiny. Metals are shiny in ways that non-metals, like your desk or this wall, are not shiny. So metals are shiny. They're good conductors. What are they good conductors of? And what else? Yeah, electricity and heat. So they conduct electricity. They conduct heat, where non-metals don't do that. And then they're malleable and ductile. What does that mean? Yes, and actually they're both kind of the same thing. Malleable and ductile means they can be bent and shaped. But specifically, I'm going to give you a hint to kind of remember these, because you will have these on test questions. Let me just stop for a second. This stuff is not going to be on the test next week. I already have the test written. We will kind of go over this again before the next 3 weeks test. But the 6 weeks test that's next week will only be the stuff that came before this, just so you know. So malleable and ductile, there's 2 words that sound like these words, and they will help you remember the difference between these terms. Malleable sounds like the word mallet, like a hammer, like a soft hammer. So a mallet can be used to hammer metals out into thin sheets. That's the specific definition of the term malleable, can be hammered out into thin sheets. So malleable, mallet, hammered, thin sheets. Ductile, this is kind of a stretch, but it helps you remember. Ductile sounds like duct tape, and duct tape can be used around wires. So ductile is a property where you can pull it out into a thin wire. And technically, those are 2 different things. In malleable, you're squishing it down to make it flat. And ductile, you're pulling it apart to stretch it out into a thin wire. You shouldn't use duct tape for wires. You should use electrical tape, but it works. Malleables, mallets, hammers, ductile, duct tape, wires. Okay? Is everybody somewhat comfortable with that? Yes. Now, nonmetals are literally just going to be the opposite. They're found on the right side instead of the left side. They gain electrons instead of losing them. So your nonmetals on the right side have close to 8. Well, the noble gases do have 8, but the rest of them that actually do stuff and are interesting have close to 8, like 7, 6, 5. They're going to be closer to getting that full 8 than going all the way down to 0. It's going to be easier for them to steal 1 or 2 than to get rid of 6 or 7. So they're going to be really good at taking electrons from your metals. If they bump into a metal, they're just going to switch electrons real quick. The nonmetals are going to have more electrons. The metals are going to have less. So instead of being positive, they're going to be negative when they take on that extra negative charge as an electron. So like chlorine here has 7 out of 8 electrons in the outermost shell. It's going to gain 1 electron to form a negatively charged anion. And then their properties are going to be the opposite too. They're not shiny like metals, so they're going to have a dull appearance. They're not good conductors of heat or electricity. So think of like a non-metal handle on a pan, like a plastic handle on your pots and pans. It doesn't get hot, so you can pick it up right off the stove, and it's not a big deal. Also, they're often gases or brittle solids at room temperature. So your noble gases are gases. The rest of them are usually solids at room temperature, but they're not going to bend and break like malleable and ductile things. They're brittle. They're not going to bend like malleable and ductile. They're brittle. They're going to break instead of bending. So that's the difference between them. They're pretty much opposites. Then you go to the metalloids. These green things right in the middle. The metalloids are a little bit of both. They kind of sit right in the middle. They're not metals. They're not nonmetals. They do a little bit of both of what they do. One of the most common ones that we use is going to be silicon. It's a good semiconductor. It's used in computers. So silicon, what is their name of the country? Not like an actual name of a city, but a place that uses the term silicon. Have you heard it before? I know you've heard it.
What? You mean like Sicily?
Silicon what?
Valley?
Yes, Silicon Valley. Has everybody heard that? Silicon Valley? Yes. It's a place in California. It's not an actual city, but it's where all the big computer companies are. So because all the big computer companies are there, they call it Silicon Valley. We use silicon in computers because it's a semiconductor. It does conduct electricity, but not fully, not the way that all the other metals conduct electricity. So imagine this over here, this computer. It's plugged into the wall. Do we want all that electricity that comes out of the wall to go everywhere in the computer? No. We want to limit it. We want to control it. We want to only allow it to go where we want it to go when we want it to go there. That's where the semiconductors come into play. They allow just a little bit, just enough electricity in where we can have delicate little parts like your monitor and your mouse and all sorts of other parts in the computer to be able to do what we want without having all the electricity flowing through. So semiconductors are really good and useful. We use all of them in all sorts of different properties. They're not as brittle as your nonmetals, but they're not as bendable and malleable as your metals are. They're kind of like Goldilocks, right in the middle, nice and perfect. So how's the periodic table divided? We have periods. Periods are going to be your rows. So remember, periodically, it's going to repeat. So your periods are going to go from left to right. And as you go from left and right, it's just going to repeat over and over again. It's going to start with your alkali metals. It's going to end with your halogens. Every single row on the periodic table does that. And it goes through the same kind of pattern. Groups are going to be your vertically aligned columns here. So note, your periodic table has the 1 through 18, like they mentioned here. It does not have the 1A, 2A, all the way to 8A, and then the B's separated. It's not real important. Your packet does have those, but the main thing to remember is when we're counting electrons for your Lewis dot structures, you have 1, 2, and when you go over here to 3, if you go to the top of the periodic table, that's column 13. So if you can remember, instead of 13 electrons, this has 3, 4, 5, 6, 7, 8. That can kind of help you out with the electron part. So they're divided into periods and groups. They're also divided into families. And the families are the names that we have in the color-coded key up top. So you have your alkali metals, your alkali earth metals, noble gases, halogens. Your pink is your transition metals. We've got them all separated out into different groups, and we're going to go through those right now, hopefully very quickly, because you're gonna have plenty of time to do the assignment. So group A elements indicate the number of valence electrons. So 1, 2, 3, 4, 5, 6, 7, 8. These columns tell you how many electrons you have. The number of electrons is your oxidation state. And this is, unfortunately, one of the worst names in science because oxidation state should have to do with what? Oxygen. Like it's what everybody thinks. Your brain is just like hardwired to say oxidation state. It's got to be like the number of oxygens that it has. It's not. It has nothing to do with oxygen. It's like the worst name that you could possibly think of. The oxidation state is literally just the charge. I don't know why they didn't call it something with the word charge in it, but oxidation state is probably before we understood what was going on, but they just kept it. So the oxidation state is the charge of an element as an ion. It's also known as the oxidation number. So if your oxidation state is positive, if your electrons are lost to form an ion, so like your metals, they give up electrons. When they give up that negative charge, they have extra positive charges. Your oxidation state is going to be positive however many electrons you gave up. If I give up 1, I'm positive 1. If I gave up 2, I'm positive 2. Your oxidation state is negative if you take in electrons. If I steal 1 electron, I'm negative 1. If I steal 2 electrons, I'm negative 2. So your reactivity is determined by your ability to gain or lose or share electrons. And we'll talk about sharing later. We're kind of mostly going to talk about gaining or losing today. But their idea is they want to get to that number 8. Everything wants to get up to 8. If you're below 8, that's not the state they want to be in. Once they get to 8, like the noble gases, they're nice and happy. So the elements that only have one electron are going to be really, really good at giving away that one electron because it's very easy just to get rid of one. Same thing with the ones that have 7. They're going to be really, really good at stealing one electron and getting up to 8 as opposed to getting down to 0. So your metals lose electrons when reacting with nonmetals. For example, what is salt? Does anybody remember the formula for salt?
Sodium chloride.
Sodium chloride. So sodium has 1 electron. Chlorine has 7. They combine really, really easily because sodium just loves to give that electron over to chlorine. Once it does, they're both super happy, and they will hang out next to each other all day long, and we sprinkle them on fries and chips and make things delicious. So your metals lose electrons, your nonmetals gain electrons. Nonmetals can also share electrons with each other, which we'll talk about in a different chapter, but we don't need to go through today. So we're going to go through the different types. Noble gases are all the way on the right side. They're the dark blue ones. They're non-reactive because they already have those 8 electrons. They don't need any electrons. They don't want to give up any. They're all gases at room temperature, so they just float around the air. We kind of have to separate them out from the air. And neon. Noble gases are used in what type of lights? Neon lights, because neon is what? A noble gas. We all use the term neon, but depending on what noble gas you have, that actually controls what kind of light it gives off. And so you can see here, helium is a different color than neon, and argon, and krypton, and xenon. So each one of them gives off a different type of light because of the number of electrons it has and the energy level that they have. So then they go to halogens, group 7A. And 7A or 17 on your periodic table means they have 7 out of 8 electrons. So are they more likely to lose those 7 or gain one more? They're going to gain one more. They're non-metals. They're really good at gaining electrons. So they're going to be great at stealing them. And when they do, are they going to be negative or positive? If they steal 1 electron from somebody else, they're going to be negative. They have 1 extra negative charge. They're going to be -1. So they're going to be really, really good at that. That means highly reactive. Anytime they bump into something else, they're probably going to steal that electron and have that -1 charge. And that term we use is electronegative. We'll get to that next assignment with the electronegative and all that stuff. So when they steal that electron, they form an ionic bond. Just like chlorine steals an electron from sodium, chlorine is now negative, sodium is now positive, and that negative and positive does what? It attracts. Negative and positive charges attract, so they're going to stick to each other and form a salt molecule. We'll talk about covalent bonds later. All right. Alkali metals, where are those at? Yeah, they're that first column in the orange all the way to the right. So we've gone from the teal all the way to the left that has 7 to the alkali metals, which only have 1. They only have 1 valence electron. What are they going to do with it more than likely? They're going to get rid of it. They're going to lose it to a different atom. When they lose that negative charge, what are they going to be? Positive, specifically +1, because they lost 1 negative charge. They will be +1 as an ion, which makes them a cation. Cat with a T, +1. Let's see. When a positive ion combines with a negative ion in an ionic compound, that's going to be called a salt. It's a generic term. We've kind of adopted it for our salt that we put on our food, sodium chloride. But any of those can be a salt. If I have potassium bromide, that's considered a salt. Any of the positives combined with any of the negatives as an ionic compound is called a salt. So alkali metal hydroxides form with strong bases in water. If you have like lithium combined with water, it's going to be a lithium oxide. So the oxides is a word that they use to combine with water. Strong bases, it has a strong reaction with anything, so it's going to be a strong base or a strong acid, which we won't talk about acids till like the very end of the semester. So alkali earth metals are the next column, and the yellow here, they have 2 electrons. They're going to get rid of both of them. When they get rid of both electrons, what's their charge going to be? +2. Now note, these are still very reactive. They're not as reactive as the alkali metals because it's much harder to get rid of 2 electrons than it is for 1. It's easier to get rid of 1, so the alkalis are going to be very, very reactive. Your alkali earth metals are going to be a little bit less reactive. But pretty much the same as the alkali metals. Now, transition metals. What colors are transition metals?
Pink.
Pink. They're pink in the middle. These are a little bit weird. And the reason we skip over these when we do the Lewis dot structures is they have a variety of oxidation states, which means a variety of charges. So if you pick any of those elements in there, like cobalt or iron, it's not just going to be like a +1 or a +2. It could be all sorts of things. It could be +4 or +3 or +2 or +1. It just depends on the element and the situation that it's in. So those dots don't really work for the elements in the middle, which is why we don't use them. Because they could be all sorts of different charges, they can form all sorts of different compounds. So you can't really trust that it's always going to be the same formula if you're using one of those pink metals in the middle. So their example here, iron oxide that has 1 iron and 1 oxygen, or iron oxide that has 2 irons and 3 oxygens. It depends on the charge that you have for your iron on how they're going to combine. They're less reactive than the alkali or the alkali earth metals because they usually have more electrons to give up, like iron, gold, copper, nickel, silver. Gold's not super reactive at all. So the last two, the very bottom down here, look what they added in to make our periodic table weird. What are those two called? Lanthanides and actinides. And they basically tell you that the lanthanides, which are the gold ones up top, are all found in nature. Note, their atomic number's less than 83, and so they're not really, there's probably some that are radioactive, but they're not all radioactive. They are found in nature. The actinides are all, they're all above 83, so they're all radioactive. And most of them towards the end there are all made by humans like in a lab. They don't exist in nature because they're so radioactive. So, nice. I think that's the end. You can go ahead and start. Use that packet and use the periodic table. And if you have any problems, please let me know. There was at least one question during third period that was literally like they put the wrong word in and the question was just wrong, so I had to delete it. So if you have any questions, please let me know. Do your best to get all the way through it. We will probably have some time to work on it on Monday, but try your best and try to get as far through as you can.